This presentation is delivered by the Stanford Center for Professional Development.
Good afternoon. Welcome to EE3A Stanford Computer Systems Colloquium, Fall 2012-2013. The course organizers are Dennis Allison and Andy Freeman, and they're both out of town, so you get me today. Today we have Richard Palmer from Juniper Networks. They make the gear that holds the net together. And the interesting thing about the network is that it's not stable. How many of you guys saw the, well, stable over time, excuse me. How many of you guys saw the Dilbert cartoon last Sunday? Yeah, it's really good. Go look it up. The buzzword is cloud wash. Yes, it's classic Dilbert. It's great. And if you have a different sense of, pardon?
He may not agree with you.
Well, the neat thing, I was coming back over from Donner Summit 10 years ago, and we took the back road for a ways, and we found a construction project that slowed us down. And they were putting a pipe, this big in. And it's not a gas pipe, it was a fiber pipe. They were just putting in a steel pipe. I assumed somebody was going to come along later and fill it full of fibers. But I did the back of the envelope calculation and came up with, if you put half the U.S. population on each side of Donner Summit, that was still a gigabit each, right? So anyway, please welcome Richard Palmer.
Thank you. So that's a great lead-in, and I was at an event actually here on campus last week called the Revolution of Software-Defined Networking, and individual in the program here came up to me and said, there aren't any problems left to solve in networking. We figured it all out. It's just, we give everybody a gigabit to their house, to their phone, and we're done. And people that design networks, and for the past about 15 years, I've been calling on end customers, big enterprise customers like Boeing, and Stanford, the university itself here is a customer of mine, and helping them build these networks out so more and more people can access more and more services. And so the challenge is not that even the first mile, the last mile, whatever you want to call it anymore, to the device or to the home. It's when it all gets into the big data centers where, run by the Facebooks and the Googles, the Yahoos, the big companies that want to serve up these rich applications. How do they manage all of that simultaneous demand, right? And part of it's called cloud computing. So let me talk a little bit about how we got to where we are, because I think it's informative, because in technology in general, but especially in networking, it's hard to leave behind what you started with, right? And big companies like Microsoft and Cisco face this problem as well, right? You want to innovate, you want to build new things, but your customers, sometimes some of your customers are just fine with what you had 20 years ago. And so it's hard to do a clean break. And although people are working on that as well as another program here at Stanford, you might be familiar with the Clean Slate program. And it's actually a group of researchers that are looking into, how do we design the network if we could start all over again? And that's actually where the concept of software-defined networking came out of. So I put up a little my view of a timeline about how network design has evolved that kind of informs this dialogue. And obviously this goes back further to ARPANET, which is where we first came up with packet-based networks, right, and Ethernet, which goes back into the 70s. But it was about the mid-80s where organizations, again, universities, big companies, started to build data networks, and they started to digitize the work of their employees, people who used to do typewritten reports, or if they were an engineering or architecture firm, they would do drawings, and people started to digitize that work. CAD and word processing were the early applications for desktop machines, and the early networking was 10-base-5, and it was a bus technology, right? You had basically one long cable, and everybody tapped into that one long cable. Pretty easy topology, pretty easy to troubleshoot. You just followed the cable along, right? Oh, there's the bad one. And in the early 90s, we actually figured out how to run that Ethernet over twisted pair wire, and the original Ethernet 10-base-T was actually able to run over what we now call Cat3, which at the time was used for business phones. And so it was very convenient. A lot of that wiring already existed in big again, campuses, whether they be academic, government, or business, and you could now run data over that existing wire. And people started to do other things with the network. Tim Berners-Lee developed the idea of the World Wide Web, initially just text-based, obviously. And people started to, obviously email has been back to the beginning of ARPANET, but regular folks, if you will, started to use email around this time. And in the early 90s was when a bunch of companies working out of the first interop IPO'd. So Cisco IPO'd, companies called that you probably have never heard of because they haven't been around for a while, Wellfleet Communications, Synoptics Communications, Cabletron. These companies all IPO'd in about 89, 90. And they wanted to commercialize these networks and build a business out of it. And so those early networks were very much for organizations, right? We really hadn't thought in terms of consumers yet. And so, and one piece, so this is Moore's Law. I'm sure people that come to classes with EE and the title are familiar with Moore's Law. But it also affects, things that we do in the network world as well, right? Because we also can leverage the number of transistors on a CPU to build bigger and faster network hardware. And so that's really the background to this whole timeline is Moore's Law, right? And this line can be not just transistors on a processor, but this is the number of routes on the internet. It's the number of hosts connected to the network. That's all grown over time. But back in, again, when these companies IPO'd, and when we first got the first Ether switch, company called Kalpana came up with that, took 10 base T and figured out how to connect a lot of users simultaneously. It wasn't too long before we started to build networks that looked a lot like this. It's called a tree. It's called a three-tier architecture. The three tiers being starting with the servers in either a big campus or data center, called the access tier. And that tier of devices connects to the next tier, which is called the distribution tier. And then in again, the so-called classic network design, you have the core. So the three-tier architecture. And based on what people were doing and how they were going about it, right, the pretty static content, static applications, a lot of file sharing, again, email, not too heavy demands on the network infrastructure. And so this design worked pretty well. The servers, again, back in this early design, these are pretty much physical servers. Server virtualization didn't come around actually until the year 2000. I should say x86 server virtualization. For the computer historians, they'll know that IBM developed that idea a long time ago, but it really became popular for commercializing on x86 environments when VMware came up with the idea to do it on x86 servers. So building on that, the mid-90s, things really started to change. The Windows 95 put a pretty useful GUI in a lot of people's hands, not just, and it started to grow beyond the business environment. Now people at home might have a computer with a GUI on it. Mark Andreessen, of course, and as part of NCSA, worked on the Mosaic browser to take this idea of the World Wide Web and take it out of just the text-based world and be able to add rich content, pictures and videos and lots of other things, and again, make it more accessible to the average user. And also kind of the beginning of what we now call the dot-com boom, right? Netscape IPO'd, taking that browser that Andreessen had and taking Andreessen and commercializing that. Netscape IPO'd, eBay IPO'd, Amazon IPO'd. So all of a sudden now you've got a lot more people want to access these rich data network resources, or actually users don't usually want to access the network. They want to access the neat stuff on the network, right? And that's where the bottlenecks happen, is that you have lots of users, which aren't really shown on my network design, and you have lots of services or servers, and it's how we coordinate that communication between all the users and all the services that makes network design a challenge. Around Y2K, of course, there was the Y2K, but we also sped up Ethernet again, getting to the gigabit you were talking about earlier, and which is, back then was really high speed and expensive, and now it's I can have it on my MacBook Air, right, with a little $29 dongle. So, but that part of it is evolving or had evolved fairly rapidly. If I had the actual dates on here, you'd see that the time between 10 base T and 100 base T was quite a while. From 10 to 1 was was a short amount of time. From 1 to 10 was very short. We now have 40 and 100. The next leap is going to be pretty tough. Again, if you follow Ethernet standards, basically you're only able to get packets so close together and have frequencies go so fast, right? Basically, when you get beyond 10, if you look at the underlying technology, really all we're doing is multiplexing multiple 10 gig paths on a single piece of fiber or a fiber bundle. So we've actually kind of, at least from a change in the fundamental technology of Ethernet, we've kind of hit a roadblock. We will still have faster speeds, but again, faster speeds don't necessarily deliver better service, especially as more users are mobile. I'm tying up 5 IP addresses here on the desk between my mobile provider and the guest wireless network here at Stanford, and so I'm not even burning up a single Ethernet port here in the room. The mid 80s, the mid part of the last decade is when things really took a very different turn. The idea of server virtualization started to be used by big companies, and of course the iPhone was introduced. And now all of a sudden, accessing the network resources has become decoupled from a physical connection or even a physical place. And more importantly, the iPhone didn't just give you mobile internet, right? The iPhone and obviously following on other smartphones, you have multiple sensors on these devices, right? I've got a camera, I've got a GPS, and so the things that I want to do, and again, a lot of creative people here and in other places have come up with apps that combine all these sensors into an interesting output, right? Things like Yelp, where I want to have restaurant reviews for the restaurant I'm walking by, right? Think about all the information that has to be processed for you to get that information, right? And that happens back in these data centers. Well, this design doesn't really hold up anymore. Again, I want to access a lot of rich content. I want to create rich content, and I don't want to have to wait for it. And this three-tier design doesn't work in a virtualized environment where the number of users is growing, far outstripping the ability of this legacy network to support it. So it was a little while ago. So this graph is showing, it was actually about 5 years ago, the number of servers that are virtual has actually surpassed the number of servers that are physical. And that introduces many challenges for network designers. Again, back in the day, if you will, with this three-tier design where pretty much everything was physical, from the switches to the storage, everything was physical. And you could actually, if there was a fault in the environment, you could pretty much go back to just tracing things. It's like, oh, it must be over here. I can just follow this piece of cable. Once you start virtualizing everything from servers to storage to firewalls, that's no longer possible. And not only is it no longer possible, but the things that people want to do with the virtual servers are different, because now I've abstracted my operating system and my applications away from the physical hardware. Why should I be tied to the physical environment? And that's, again, opened up both a lot of possibilities for application designers, but it's opened up a lot of challenges for network designers, because we can no longer count on that server remaining where it is physically in the data center. It could be across the data center, it could be to a backup data center, it could be across the country, following the user demand. Another element that has really altered the way that networks are designed, if you looked back at that tree architecture, it really was designed with, going back to the first networks, which were about campuses. It kind of had a geographic basis. And the first networks were to connect knowledge workers to a fixed set of resources, whether it's email servers or file share servers. And people thought in terms of, well, I've got floors on a building, I've got buildings on a campus, and then I've got a campus core. And that three-tier architecture followed sort of that geographic mindset. Well, as you can see, this is currently how large data centers, the percentage of traffic and where it's going. So that really big slice is actually traffic of servers talking to other servers, or applications talking to other applications. So I gave the example of Yelp, and again, you could think of a lot of applications that, in order to serve up the content to you, your Facebook page, they're pulling in ads that they think are relevant to you. They're pulling in your friends' updates, right? There's a lot of processing that's going on before it's presented to the end user, and that processing happens within the data center, and before it ever is handed out to you. So if I've designed my network with this geographic mindset where I've got a bunch of users accessing a fixed set of resources, that the old 3-tier architecture, it's very inefficient, because you have to, what happens is a lot of my traffic, we call it east-west in these larger data centers, a lot of these applications are talking to each other before they deliver up the results to the person that requested it. And this tiered architecture is very inefficient, because in the old days, we would have a given number of servers on a subnet, and if you wanted to talk to a different server, you had to pass a routing boundary, or what we call a layer 3 boundary, in order to get there. And in networking, usually the higher up the OSI model that you go, from physical to link layer to IP layer, and the higher up you go, usually the more CPU cycles it takes to do any interesting processing. And so if I just want to, again, collect all this data, I want to look in a database, I want to pull up some video files, some static pictures, and serve that all up as unified content, I want to keep the processing to a minimum, so you're not sitting there waiting for this to happen, right? Again, it's a very competitive digital economy now, and those that provide the best servers are going to have the most users, whether they're paying users or whether they're eyeballs to sell to advertisers, right? It's a lot of competition to provide that user experience. And so this model breaks down. I put this up here just again for those that aren't. I know most people have virtual machines on their laptops now. I'm sure this is pretty common technology, but I wanted to just put it up as a reminder. What is a virtual machine, and also what is vMotion, which is what virtualized environments want to do with those virtual machines is not just leverage the horsepower on this physical server, right? So, why has virtualized x86 servers become popular? Again, getting back to Moore's law, especially legacy applications that were written for, say a CPU of 10 years ago. If the application hasn't changed much over time, and now I can get a server with 64 cores and 128 gig of RAM, it's going to have that physical server about 0.5% utilization, which is a huge waste, which is what drives people to virtualize. And once you've done that, now you've opened up. First of all, you get, from an economic perspective, I've got better utilization on my physical hardware. But now you say, well, why should I be tied geographically to where the physical hardware is? If I want to have a load sharing environment so that I can again follow the sun. If you're a global company like Facebook and Google, I want to have some of my application servers move around real time. I want to do it for backup, and I don't want to have to shut down the OS in order to do that. It's called live migration, or vMotion. And that puts, again, a new kind of stress on the network. This technology, the way it's been developed so far, actually doesn't work across layer 3 boundary. So I need to enable my layer 2 environment to stretch much broader than it ever did before. And again, having to cross those layer 3 boundaries doesn't support this technology, but it also, the latency that it introduces is detrimental to the environment as well. This is sort of re-emphasizing the idea of east-west traffic. And again, it's hard to overemphasize it, because that's really what's driving some of the things that I want to talk about the challenges that the industry and academia right now is trying to figure out about how we enable these things. Because the things that we're doing today, they're solving part of the problem, but there's still a lot left to do. And sorry. Here we go. So we have this virtualized data center. We have companies, again, like Facebook, like Zynga, and even big enterprises that want to be able to move their services around the network seamlessly. it's the current architecture, both network architecture and even the virtual architecture, if you consider virtual LANs, wasn't built to scale to the numbers that people are trying to support. And I tried to sort of consolidate a bunch of different things that people are doing to solve different elements of this virtual data center. The first one is the virtual switch itself. And so if you think back to that layer, I'll just put it back up here. So this is the way that most hypervisors work, and I'm using VMware as an example. Obviously, there's other people that make hypervisors. So this piece is actually a virtual Ethernet switch. So not only have I taken the servers and virtualized them and put them, many of them, and this is showing 3. I think the average is 12, but some environments, they have up to 100 virtual machines on a single physical server. And the first network hop is actually inside that physical server. And that introduces a couple of challenges. It introduces the challenge that VMware is not really a networking company. I mean, they've done a decent job, but that's not their core skill. And so what happens is that it's typically that device they're providing, that virtual switch, isn't managed like a regular switch. And also from a organizational perspective, in large organizations, right, the network people are their own domain and server people are their own domain. And there's the question of, well, who configures the switch on the server, right? And it sounds maybe kind of trivial, but again, in big organizations, it can be very contentious. And even if it's not contentious, the server people, again, it tends not to be their sweet spot either. And they might make decisions about, well, I'll turn this feature on and I'll leave that one off, that might create chaos in the greater physical network. And so we're trying to figure out, again, as an industry and as a community, how do we address this problem most efficiently? And like most things in networking, there are competing approaches. Just for the virtual switch piece, that's my first two rows up here. There are 2 sort of global approaches, and then there's 3 implementations within that. And they're all, actually 2 of them are standardized, although they're not very well adopted. And the first 3, what are called network overlay technologies, are they're working their way through the IETF. One is it's actually 2 of them, since this company, I don't know if you heard of a company called Nicira. They sort of put the idea of virtual networking and software-defined networking on the map because VMware spent, I believe, a little over $1 billion to acquire them about a quarter ago. So before they did that, they were driving this overlay technology called VXLAN, which does a couple things. It tunnels that virtual machine traffic across an existing network, and it also extends the number of virtual LANs that are available in the environment. So if you're going to have hundreds of thousands of virtual machines, the traditional limitation of 4,000 virtual LANs just doesn't really hold up. So, but it's an approach. Again, it hasn't been standardized yet. There's impetus behind it, but you might know that Microsoft is trying to get back into this game. Obviously, they were and obviously are a big server player, but in most server environments, virtualization is very important. So their solution called Hyper-V has its own virtual switch, and so it needs its own network overlay technology. Again, the startup called Nicira was working on a 3rd one. Now they're part of VMware, so it is yet to be seen how that's going to play out. So that's the network overlay is again one part of the problem for one set of vendors, if you will. A different sort of the problem that I spoke of earlier. Who's going to manage this virtual network? That's a couple of different vendors on the physical hardware side. Both Cisco and HP are leading the 2 things called Ethernet virtual bridging, and that is basically disabling, if you will, that virtual switch that VMware or Microsoft or whoever the hypervisor manufacturer is, and doing all of the switch processing, whether it's spanning tree, whether it's layer 3 on the physical switch. And so, again, these technologies, which were standardized by a different standards body, and again, for people that are only peripheral to networking, there's basically 2 standards organizations that help drive things in networking. The IEEE, which obviously is responsible for lots of things beyond networking, Institute of Electrical Engineering, They do a lot of electrical standards. And the things that start with 802 are usually related to something to do with Ethernet. And as you can see, by the 3 letters after the number, we have all the standards we can eat at layer 2. So, and on the internet side, so IETF, Internet Engineering Task Force, that's where things around the IP protocol tend to be standardized. And it's a different process, and you know, both of these, even though they're standards bodies, you probably know standards bodies tend to be occupied by the same people, right? So a company comes up with a technology, they get first mover advantage, and then you know, after a while they decide to go out and, well, maybe I'll standardize this and make it a little more popular, right? That tends to be how standards happen, is either industry and sometimes academia. Again, you'll see some, and I don't have them on my list here, but in the IETF, there's several SDN standards being promoted today, and those tend to come more out of the academic side of the house so far. So that's the virtual switch. Again, sort of a subset of, you know, how do we address the needs of the virtual data center. And the next one is what we call data center fabrics. And just sort of an illustration of what we mean by that. So it's contrasted to the 3-tier architecture I showed earlier. So I eliminated a layer, and that's part of what a data center fabric is. But the other part of it is I need to deploy different protocols. And I'll go back to what some of those are, so that I can eliminate the traditional protocols in my 3-tier architecture, which tended to disable about half the links in my environment. If I'm going to have an effective data center fabric and be able to move those virtual machines throughout the environment wherever they need to go, I need to, again, flatten the fabric and speed it up and be able to leverage more of my links. And so that's what I mean when I refer to data center fabrics. I'm showing a couple of different competing architectures. QFabric is the one that Juniper's working on. This is the Trill architecture is being worked on by some of the other big players in the industry. HP, Cisco, and Brocade are working on Trill approaches to data center fabrics. So here's sort of the vendor approaches, if you will, to data center fabrics, and those are all I'll call them brand names for solutions that the vendors sell. There's actually both an IEEE and an IETF standard for this. The IEEE one, this is, SPB stands for Shortest Path Bridging. That one actually has not been finalized yet, but you know, and maybe it'll alter how we do things. And then Trill, and some of these manufacturers will say that their solutions are based on Trill, but unlike some of the existing standards like Spanning Tree, nobody's Trill talks to anybody else's Trill today. So it's definitely exactly. It's a very customized standard, if you will. So, and the third piece is of supporting the virtualized data center is what we call data center interconnect. And what I mean by that is, you know, we've always had wide area communication. Obviously, the original ARPANET looked something like this, right? We connected various research institutions across the country with the original ARPANET to pass traffic. But you know, TCP/IP was standardized pretty early in that environment, and things, when they went very far, everything was a layer 3 hop. I looked up in the routing table and I forwarded it to the next hop, and I looked it up in the routing table. And again, to build out these virtual environments so that this virtual machine can do live migration from my primary data center to my backup data center, I need to have a layer 2 construct across this wide area boundary. So there's currently one standard, and it's a VPLS, and it's virtual private LAN service. It's layered on top of a MPLS circuit that you can get from your wide area provider. And that's one approach. It definitely works, but there's a lot of room for improvement. So again, going back to my slide, my room for improvement slide. So there's a couple different approaches that these are all very proprietary. Cisco has a couple, one's called OTV, one's called Lisp. HP came up with one called EVI. And then VPLS, I mentioned, already exists, and that one's pretty well adopted. And there's a couple of new ones called MAC VPN and Ethernet VPN. So trying to address some of the shortcomings of VPLS that to better support these virtual environments. So these are all obviously trying to address a single component of the overall challenge, right? So, and they all come at it with the basic philosophy that networking has always followed since, again, the development of the ARPANET really, is that we're going to have a distributed environment, and so therefore we need to every device in that environment needs to have some sort of protocol to talk to other distributed devices, share state, figure out how to forward a random packet, right? And so the things that we're layering on top all still follow that basic premise of how networks are designed. And again, coming out of the Clean Slate program here at Stanford, there's been another approach, which we call software-defined networking, which says, let's take a completely different look at this. And it says, this is how we've been building data packet networks, again, since the ARPANET, with these three ideas as the basic premise. And this still applies to all the emerging standards that I just talked about, whether it's VXLAN or OTV or whatever. They're all still following this basic concept of, for the data plane, every device has to make an individual decision about every packet that it sees. And it's going to do that based on some control plane algorithm, whether it's a routing algorithm like BGP or OSPF, and I've got to communicate to my peers if the topology changes. And really probably the biggest challenge is what we call the management plane, and that is somebody's got to configure all this, right? And it's kind of cumbersome, and more importantly, in the virtualized data center and the virtualized network, it's not really allowing innovation. I mean, there's obviously the things that all the vendors are working on and they're innovation of a sort, but the network really is a service, right? The network is, some of us call it plumbing, right? We want it there, but what we really want is the application, right? What we really want is the GPS app to work. We want our Facebook to update. We want to be able to get the Giants score when it starts in half an hour, right? We want to be able to get these services off the network, and we want the network to be transparent. And the people that are developing the applications, they want to consider it as a utility. They don't want to have to think about, well, how do I get my application to the head of the queue, or how do I make sure that it works across this virtualized data center? And so software-defined networking, even though it has software-defined networking has defined in the title, but there's actually a lot of definitions right now. Again, the industry is all still trying to figure out what it's going to mean long term. But I found this is actually put together by somebody at Princeton, and this is a really good presentation that I found. And it really takes a sort of a fundamental approach to explaining software-defined networking and contrasting it to traditional networking. And this is really at the most fundamental level what we mean by this. And it's abstracting out all that control and forwarding intelligence up to a software layer. And pushing out and have the forwarding devices just have an API to this. And again, the vision is, and that's kind of where we are, there's obviously some labs going on, and there's definitely, I mean, Google made a big splash, right? They're doing some things with data center backup with OpenFlow, which is one implementation of software-defined networking. But so far, it's still very much a fluid concept about what it's going to mean in the long term. But what the vision is that the application developers can now start to write application things. Again, like one of the examples is load balancing. So someone wrote a software-defined network application, and they were able to push it out to this research network. Actually, the Internet 2 is the network they're using. And he was able to even out the spikes in server requests just by writing this app, right? And obviously, it's still a research environment, and meaning that we haven't really proved that it's going to work at scale, but it's a very interesting concept, and it could fundamentally change how we build networks. And again, take it out of the hands of companies like mine and put it into the hands of the software developers. But it's yet to be seen where it's going to go and what form it's going to take, because all of the network manufacturers are all on record as saying we support software-defined networking. But obviously, everyone's trying to figure out how do we take something that wants to be open and free and widely available and so forth and make a business out of it? And I think that's where the conflict's coming from. So so basically two competing approaches to try and address the virtual data center. And I just wanted to go back briefly to the data center fabric, which is what I probably spend most of my time talking to customers about. This is whether customers are virtualizing, and actually some customers, big companies, actually they don't virtualize. But even if they're not leveraging the virtualization technology, that probably means they're buying more servers. And so they still have a scale challenge, which is how do I connect more of these devices, make their services readily available without being affected by latency. Again, back in the 3-tier architecture, latency it really inhibits the ability to write robust applications. So if you're building out a bigger website or a bigger application, you're going to have a web tier and an app tier and a database tier. It's kind of the classic tiers. And what happens, whether you're virtualized or whether you're physical, those tiers of I'll call them sub-applications, want to talk to each other. And if they have to be hindered by an intermediate hop that's going to slow them down, they tend not to work as well. A lot of these apps are written with the idea that perhaps they're on a given physical server, and latency obviously it can be measured in nanoseconds. And if I spread them across a network and I introduce latency, now the apps don't work anymore. And so data center fabrics are interesting to customers, again, whether they're using virtual or physical servers. And today, if you walk into any given data center, the people that are virtualizing tend to have the big blade type servers. People that are not tend to get what we call pizza boxes, the more economical, almost disposable, I'll say, types of servers. But the scaling is a challenge on either front. And so one of the approaches is what we've done at Juniper is taken the idea of a physical chassis switch and expanded it to support a data center of 6,000 devices. And so we call this QFabric. And what we've done is, again, taken the concept of a physical Ethernet switch, chassis-based switch, which has been around for about 20 years. And all these devices have some sort of an internal switch fabric. They have the modules where you plug in the Ethernet connections. And then they have some sort of intelligence, whether it's called a supervisory module or a route engine. And all these pieces slot into the same sheet metal. And the control protocols and the forwarding tables, the control protocols are managed as part of this routing engine. And based on the calculations of the topology, they push out that information to the line cards to do forwarding. The challenge, obviously, with a given piece of sheet metal or a given PCB with traces is that you can only get that so large, right? Typically, so far, it's like 42 RU is about the biggest one I've seen, right? Once you get beyond a given rack in a data center, it's you need to come up with something else. And so the approach we took was, well, let's abstract this idea of a backplane out and make it a separate device, and let's make it optical instead of electrical. And let's take this idea of a line card and make that a discrete device that's going to connect to the backplane or the interconnect via 40 gig fiber connections. And let's, on top of that, again, in a traditional chassis-based Ethernet switch, most of the control protocol happens, again, on the backplane. It shares the switch infrastructure with the data packets. So there's some of the packets are user information or applications talking to applications, and some of the data inside this device is the control protocols. I get a spanning tree update, I get a routing update, and so control and data are interleaved. When you want to scale to 6,000 devices in a data center, 6,000 servers in a data center, that can be a lot of control traffic. And so another innovation that we took here was to split that off into a completely separate network. And so control does not share this high-speed data network. We just forward what I'll call user traffic or application traffic on that. And so in that way, we're able to provide that low latency that these applications are using. And so this is showing the interconnects, and this is the top of rack devices. And by building basically a very large abstracted Ethernet switch, I can now support applications across an entire data center and serve up that low latency that, that these applications are looking for.
Could you go through this again? I don't quite understand it. What's in that interconnect box?
Absolutely. So you understand the traditional chassis-based Ethernet switch? Yes.
I think so.
So if you see QFabric, this looks a lot like a traditional chassis-based Ethernet switch. It has, these are actually 40 gig QSFP ports on the front, but another way to think of it is it's a very simple core and an intelligent edge. And the processing is, again, put off on what we call a control Ethernet network. And so the routing updates, switching updates, multicast updates, they're going to, obviously, they're going to hit this intelligent edge. And control traffic is going to be off on a gigabit Ethernet network to the intelligence, to the we call it the director, but call it the route engine or the supervisory piece of the environment. It's going to do the calculations, and it's going to push the forwarding updates out to all these elements, again, via the out-of-band control network. And if I then get a user packet, a true data packet, the decision about where it's going to end up is made here at the intelligent edge. And so there's very little processing that happens here. This device knows where it wants to go. It knows the topology, and it's going to have a proprietary header on top of the Ethernet frame. And basically, this type of device is just a very simple. It comes in this port and out that port, so no other packet processing.
So there's a crossbar and such in there.
Exactly.
It's
Exactly.
Just the control logic has been simplified.
Exactly. And that allowed us to scale, again, beyond what you can put in one physical 42 RU rack.
The yellow lines of fiber?
They're 40 gig fiber, yes.
So I have essentially an all-optical switch in there.
Exactly. Exactly. Which is how we make it so low latency.
So that interconnect does not turn the bits into electronics. It leaves them as photons.
Actually, I think we do. I think it does go optical,
okay.
Electrical, optical. Yeah, it's not. There are devices, obviously, in the network space that just
you can do it
switch light. This
not,
is not. Yeah, we don't have a bunch of little mirrors inside.
Thank you.
But yes, so.
There have been many questions otherwise.
Yeah, no, it's absolutely.
Yeah.
I'm aware of there's a few devices on the market that do that. Ours is not one of them. We do make that conversion. It introduces very little latency, though, and so.
So is that node an end user device, or is that a device an end user plugs?
Exactly. So when I say end user, I'm usually it's a server.
Yes.
These are gig and 10 gig ports, so. It's more of a data center solution. I mean, you could put it in. You could hook up your desktop in a campus environment. We haven't seen it used that way yet, and that's mainly because of currently the 40 gig can go about 300 meters, so it's still pretty much within a data center type solution. In order for us to serve up the low latency that is kind of required for both of it, for it to be economically compelling, but also for it to work. The distance limitation is, again, about data center scale. So the servers hang off of this node. And again, if you were, see this a picture of it, it looks like a 1U top of rack Ethernet switch. And actually, the devices that we're using, they actually can have two personalities. They can actually be a standalone top of rack switch, 1 to 10 gig, with some 40 gig, or it can be what we call a QF node in this environment. So, but yeah, the node is where the servers attach. We also, I didn't really get into it. I didn't want to try to boil the ocean, but another thing in the virtualized data center, and you saw it back in the tree environment, is storage used to be a separate network. Another thing that's happening is that storage is also becoming virtualized, and storage and network are starting to converge on the same infrastructure. So there's protocols like FCOE that are supported here. another reason I didn't talk about it is that although the market, this is an area where I think the market's a little bit ahead of the customers. That customers are a little bit wary about intermingling these two types of traffic. So if you've ever worked with a storage area network, it's much more sensitive to loss because in a storage area network, it's actually doing block level copying. Ethernet's always been best effort, and so block level copying and best effort don't go together real well. But we both Juniper and the other players in the industry are all building these converged switches, and we're sort of waiting for the end users to catch up with us. It's a little bit like I've heard people compare it to when IP telephony first came out. The people at large organizations who are running the TDM voice network, very proprietary about their PBXs, and when Cisco and Nortel back 12 years ago came in and said, hey, we can just run that voice stuff right on your data network. The people who've been running voice for a long time said, you got to be kidding me. So, but of course nowadays most corporate phone systems are running over an IP Ethernet network, and so this convergence of storage and network I think will happen over the next 5 to 10 years as well. I think. Well,
Could you, now,
sorry?
dumb and fast, there's another interesting word there, which is inexpensive. Now, back to the previous slide. No, other back.
Uh-oh. What did it look like? Oh, I'm sorry.
No,
Skip
further
it.
back with one.
That one,
This one.
yeah. So these dumb fast switches, are they also inexpensive?
So that's a great question. A lot of times when people talk about network solutions, those are usually the three components, right? You have to pick two, right? You want, in these examples, you want scale, you want speed, and you want something economical. And you can pick any two, right? So far, the people that are coming to market with, and so far this is the OpenFlow piece of software-defined networking. They are very, I'll call them rudimentary. So, and they tend to be less expensive than say Juniper or Cisco's or Brocade's kind of enterprise class switches. They put an OpenFlow stack on there and merchant silicon, and so they don't support a lot of these features that we used to support, right? Again, all these things take, obviously they take the network operating system code, whether it's iOS or Junos, and they tend to take extra silicon beyond merchant silicon, right? All of the big manufacturers create their own ASICs to be able to do these things quickly. And so that absolutely drives up the cost of these switches. And so the approach here is that, well, let's not do that on the switch. Let's do it up here. And so there's a couple of startups that have come to market with this. One's called Big Switch. Again, it actually started right here on campus. HP has a couple of devices that do this, and there's a couple of other, I believe, Korean startups that have what they're selling as OpenFlow switches. And so they do tend to be less expensive. They're probably not consumer grade prices, but compared to traditional switches that are sold to enterprises and data centers, I'd say probably half of that, 50% less. So, but the promise is that, at least for the people that are pushing on OpenFlow, is that this is what we call merchant silicon, meaning Intel makes a switch component. There's no OS. It's just basic forwarding, and then they sell it to people that want to productize it, put it in sheet metal, and sell it as an Ethernet switch. OpenFlow so far is it's an open source protocol, right? So yeah, if people that are doing this, these are very, very low cost devices. So, but so far, as far as I know, there's again a lot of interesting research projects going on, but this is definitely in the science project stage. So, which is a good thing, but it'll have to be pushed into, I think, real live customer networks before we can see how it works over time and how it works at scale. So
What part is the science part?
So the science part, so I guess I wouldn't call Google's backup network a science project, but so most of the examples that I've seen are, again, they're on Internet 2, and they are very controlled trials. So I guess that's the piece that I'm calling science, is that I haven't seen anybody yet try to deploy a 1,000-node data center.
It's not very robust yet.
We haven't tried it yet, right? So I'm not saying that it can. It's just nobody's tried it yet. People are there. We're very much in the proof of concept stage. Again, I think there've been like 2 OpenFlow/SDN conferences, and we're very much in the early phases. And again, there's a lot of cool videos online from the Clean Slate Institute and the Open Networking Foundation. They kind of show you what they're doing. It's just fascinating, but all of them are 6 nodes. So that's why what I say is people are just kind of seeing what's possible, and getting to the scale piece of it is going to be the next phase, I think.
Just thinking, I'm thinking, work with people in photonics, whatever. Intel is starting to talk to them about fiber to the CPU, to the big chip. So what are you going to do then?
That's a good question.
Well, is that the right approach?
Right.
I'm still actually questioning just dumb and fast. Does it always have to be together? Depends really on the technology you're using. You can put some smarts in there that might be very crucial.
Absolutely, and there's
Your whole latency story. I've Google Fiber at home, and latency is the big thing, but I can trick them by turning on iTunes, and then everything speeds. All the latency goes away. So somebody cheated.
So I think what again, these are I should have given credit to the lady at Princeton who put this together, but I think what the dumb is contrasting to what the devices today are doing. Again, enterprise class switches, they're making all these decisions on every given packet, right? They're filtering, they're adding quality of service. They're, maybe high-end switches can copy a whole stream of traffic, right? That takes CPU, that takes more silicon, right? We do things like S-flow and net flow on switches, right? So we want to meter what we're doing. We want to show you what the traffic profile looks like. So I guess that's what I mean, contrasting sort of a so-called intelligent device. These so-called dumb devices, they don't do any of that. They rely on the controller or the application to make most of the forwarding decisions. A little bit like QFabric, where the forwarding piece, the forwarding logic is not on the data plane. The data plane is just, it sees it, it makes a few modifications if need be, if it does multicast replication, for instance, but we try to keep the processing to a minimum and let all the packet processing to a minimum and keep the control processing on a separate device. Again, I think that's the promise here. And what makes it interesting is that, yeah, you pull the intelligence out of here so that you can afford to have, rich applications up here. One approach. Again, Juniper, we actually have our high-end routers have an OpenFlow stack, so it doesn't necessarily have to be, but I think if you look at people that are talking about why do I want to do SDN, it's because I want to bypass all the complexity that not just Juniper, but any high-end router manufacturer has to put in to be able to support large-scale routed networks. So they're definitely competing philosophies. And even within, like, my company, I talk to the router guy and I talk to the OpenFlow guy, right? And they don't speak the same language, have the same vision. So, and even I go on Cisco's website.
Hammer of Babel.
It kind of is. It kind of is. I mean, you go to Cisco's website and they got one guy talking about VXLAN, and then you've got their CTO of cloud talking about, and you don't get the sense they work in the same building. So it's very interesting about where we are today. And that's why I say, and that's why when my colleague Benjamin talked me into doing this, it's like, what do you want out of the audience? And it really is. I disagree with the individual who said, we're done. We figured out networking. I think it really is a Tower of Babel. I think that, and in order for us to scale and keep enabling the digital economy, we need to figure this out and make it smarter, faster, and cheaper, because people want more all the time. And right now, more and more people are seeing the network as a hindrance, not as an enabler. So,
how do you handle congestion?
In this? So I'm by no means an application developer, but I did watch this cool demo on YouTube. And again, what this individual did using some OpenFlow enabled devices on the internet too, he wrote this application, and they showed a graph of a lot of variability in latency and response time to web requests. It was very spiky. And he wrote this application, and somehow it imposed load balancing. I mean, again, I just watched a video, right? I didn't read the white paper yet, but and so there's before and after. After, it's just this nice smooth line. It's, it's constant latency. So I don't know how he did it, but the idea is that
tasks are very predictable, and you can say effectively the schedule.
Yeah, but these loads are fractal, and you can't. You have to compensate on all time scales from milliseconds to days. And
that's why he cheated.
Yeah, absolutely.
And so the days happen in the red block, but the milliseconds, I suspect, have to happen in the switches.
Absolutely.
That's why I thought needle better than dumb.
Yep, and exactly, which is why I'm calling it a science project.
Dumber.
Which is why I'm calling it a science project. I mean, the person who did this proof of concept, it was a handful of clients and a handful of servers and a handful of switches, and so it's definitely still in the research phase, and it might not scale, and we have to go back to all the competing standards for virtualizing the data center, virtualizing the virtual switch, and those things. So that's why I think they're pushing both simultaneously, or we are.
Yeah, I kind of alternate years between whether I'm worrying about network performance or security, and right now, if you want a 10 gigabit intrusion detection thing and you have a spare $250,000, you can go buy it, as opposed to, a spare $50, you can buy a switch that'll do that performance.
I thank you for bringing that up. That was actually, I had that as part of my talk, but it was going 3 hours when I first put it together.
Yeah.
Because, my background, I did a lot of network security, and Juniper does a lot of network security as well. And that was the whole thing, right? But to your point, when they developed the ARPANET, the basic premise was that you trusted everyone.
Yeah.
And obviously, we're kind of at the inverse of that now. We don't trust anybody on the network. And so a lot of these things, that's a great question, a great observation. None of those virtual networking standards are taking into account security. It tends to be still an afterthought. And so I think to really get where we want to be, when we start developing these standards, whether they're Trill, whether they're EVPN, and even though EVPN has VPN in the name, it's not private because it's encrypted, right? It's private because it's sort of masked, if you will, right? Which is, for security people, it's like, that's not really private. So it's actually a huge issue, and you're spot on. It gets back to the economics, right? The more processing, the higher you go in the OSI model, which you have to do for intrusion inspection, you need more CPU cycles. But I think we need to take, as an industry, a different approach and start baking security in how we do things. And I don't think we've done that yet. So it's a very important point, I believe.
And one thing that's been bothering us a lot lately is if you go take anybody's cloud farm out there, you can't just go look at the north-south traffic going to the outside world and protect that. That stuff, maybe we can scale enough to get some control over it, but the amount of east-west between all the ugly things people are running on Amazon, for instance, how much can you let them talk to each other?
So that's another excellent point. So actually, this slide I took out of one of my Juniper slide decks, and the topic was, and I actually modified it because I just wanted to show this simply. We actually make a product that sits here. It's a firewall.
Yeah.
And so but it's still, from an industry perspective, it's kind of an overlay, if you will, baked on top of this. We should somehow, I totally agree, we need to bake it in. As we're coming up with new standards like VXLAN, well, how about a security component? We tend not to think in those terms. Today, security tends to be an afterthought, which is great for startups, right? There's a lot of security.
Still an afterthought.
Right? There's a lot of great security startups because there's so much opportunity because people don't think to bake it in at the beginning. But I think that if we, the next iteration of standards, we should probably think about, let's think about privacy, and let's think a little bit more about hashing so that we have the integrity. And I agree, it's definitely very much after we build this big fast network. Oh, wait a minute, where'd my information go? Right. Nobody wants to be in the news, right? I just lost 100,000 user IDs. Ooh, bad. So no, it's a great point. So that's all I had. Any other questions?
6,000 nodes, that's large, but it's not very, very large. What do you do beyond that?
That's a fabulous question, too. So that's 6,000 10 gig servers. And you're right, there definitely, we've actually already talked to a few customers that have big rendering farms and environments where they want more than that. So especially if you, I'm more familiar, as you might imagine, with Juniper's technology than some of the others. But so with the technology what we have today with QFabric, I have a maximum of these 4 of these interconnects and 128 of the nodes, which is how I get my 6,000 odd servers. There's no reason that this architecture can't scale beyond this, right? So today these are 40 gig links. They can go to 100 gig, right? There's no reason I can't have more interconnects and more nodes. I should say there's no technical reason. The R&D budget to get from this to the next level is considerable. And actually, to date, believe it or not, I agree there's environments where they need more than 6,000. The addressable market, if you will, for 6,000 at a time is pretty finite, at least so far. And so Juniper actually, this pretty big R&D investment in this solution. So I think until we have run into enough customers that max this out and connecting 2 together is not viable, that they need the next level of iteration, it'll probably be a while before we bring it to market. But I think the fundamental technology will scale to, when we initially launched the product, actually, we were talking about when this goes to 100 gig and going to more interconnects and at least to 10,000 nodes. So we've kind of got the sketches, if you will, of how to get to, I'll call it double that number. Beyond that, it's a great question. So, but if you need a network that big, come talk to us, and we'll go talk to the product guys and see what they can do. So, but right now I know what's slowed down, at least our development is what we've seen so far is that even the consumers for a 6,000 node environment like this it's been pretty limited so far. So, other questions?
So there's this fundamental problem of you got to do something when a link is overloaded.
Right.
And there's always links that can get overloaded.
Absolutely.
So are you dropping packets, or are you pushing back to the guy, further upstream saying, wait a minute?
That's another great question. So in so
It's a question I meant to ask. I'm sorry.
So there's a couple different things. So we have a couple different versions of this node, and one of them you can have as many connections to the interconnect as you have connections to servers. So 0 oversubscription. And so at least from I know what you're saying. I know what you're saying. You can still if more requests can get to the end node device.
Well, if I've got 3 servers all sending to the same, it's going to be a bottleneck someplace. It just may not be a bottleneck in your backbone. It'll be a bottleneck right at the connection to that server.
Exactly. No, absolutely. But so there's 2 levels. Absolutely. So there was one I was getting at was that we can design this. So the default design, the 6,000 servers actually is 3-to-1 oversubscription. So we're assuming that you're not trying to push. You're not an HPC at 6,000 nodes. Obviously, if you're going to be a high-performance compute cluster, you want 1-to-1, and we can support that, not to 6,000 nodes. But yeah, so to your point, I mean, this is an intelligent edge. So what I mean by intelligent is that we can do QoS and so forth. So, but yeah, at the end of the day, if more requests come in than don't come in, then yeah, packets are going to fall on the floor. Absolutely. The default design is oversubscribed, and so again, with the design assumption is that you're not going to have all these servers running at 10 gig, 100% of the time. So I guess from that perspective, it's no different than going back to a bus-based network, right? You have to back off and go higher up the stack and retransmit and all those things. So I guess from that perspective, there's the magic of this is that we can have a much larger L2 domain and have it spread across a larger environment at low latency. But the reality of oversubscription still exists, and the reality of you have to drop packets at some point. So Yeah, we haven't altered that calculus yet.
How does it impact your latency distribution? Will you get now catastrophic latency?
If more requests come in and then we can process at the same time, you mean?
Will the picture overall improve with your approach, or will it get worse? Can you say that already? Or as I said, what I practically saw with the Google network,
Right.
it definitely got dramatically worse.
Right.
That may be the way they did it. I'm not sure if.
Right.
Well, but what
Well, the
I
mar-
have my work around it. But anyway,
Right.
that basically means it may not have to be that bad. There's more opportunities to screw up if you wish.
Right.
So I just wondered what you saw so far, that you predicted you'll have a typical behavior you're familiar with, or will it get better or worse?
So I think for environments where they're facing that a lot, that since you can design it for no oversubscription, that at least in that environment where I have as many connections in as out, so I don't at least oversubscribe this device, I do put it back on, at least back on the server to moderate the requests and the replies. So I'm going to say it's better, because I can be a low latency, transparent transport, and I can be not oversubscribed. So I'm going to say that part's better. But you're absolutely right. It's still possible for the servers to make more requests than could be processed by the network. So.
But then you can pass the buck. It's not your problem.
Exactly.
I think internet protocol sometimes make it so that when the load increases, the throughput goes down.
Because of windowing, right? Sure. Yep. And that's what most networks are counting on, right? The network's counting on.
It's the old Ethernet.
Exactly.
Dying.
Exactly.
Yes.
The network is definitely counting on higher layer protocols to exactly to back off the requests.
Yes. With protocols that tell you to do one thing and reward doing the opposite.
Exactly.
So the other interesting can of worms in recent networking is buffer bloat.
What do you mean by that?
Moore's law is gone overboard. You can now get low-cost devices
Right.
that have seconds worth of buffering.
Right. Right. Absolutely.
And the infrastructure doesn't do the right thing. So I've measured 6-second round trip time on my simple little DSL line.
Wow. So I haven't heard of it, that terminology, but there are customers, some of these big social networking companies, for example, their applications use something called memcache, and it definitely pushes the boundaries of the buffer space on a standard Ethernet switch. And there's been a couple startups in the networking space that have built products just to address that. But like a lot of things, going back to the software-defined networking slide, it's hard to do that with a dumb switch, because buffer on a switch is by definition it's silicon, right? So you got to add memory, you got to add something to be able to store those packets. So Juniper so far hasn't really come up with what people call a deep buffer switch, but they do exist in the market. So it's not going to solve all the problems, but
No, that's the point. It makes it worse.
Okay.
If I don't have a lot of buffering,
Right.
then I can't build up the queues so that they get in my way.
Right.
It's when I have something like voice traffic coming through,
Right.
okay, but somebody poked the browser button and the browser opened 47 connections,
Right.
okay, and all of those guys dump a big pile of crap in here, and the switch isn't smart enough to figure out that the voice traffic should jump ahead of all that crap.
Right. Right.
Yep. The infrastructure is not tolerance savvy.
Right. So there's a couple, you've probably seen a couple different, there's customers, I've seen a lot of customers, they deploy voice over IP, and the whole promise was supposed to be that you could have a shared infrastructure. I've seen a lot of customers, it's like, yeah, I don't want to do that. They have a voice data network and a data network, just for that very reason. But the environments I'm talking about with memcache tend to be data centers. There tends not to be a lot of voice. But for a mixed environment, it does get back to the doing QoS processing and ingress and giving voice priority. So again, not perfect, but which is why some people are building dedicated voice Ethernet networks. But yeah, there's no question that's an ongoing challenge based on how we've built up this technology.
It looks like most of what you're doing here is meant to scale for inside a data center.
It's another great point. You're calling me out all the things I thought about that I couldn't figure out how to put in this. So my background is I've done what we call enterprise networks, data centers and campuses. Absolutely. So all these devices, especially the ones that are on AT&T and Verizon's network, right? There's a whole other piece of the network, right? That's mobile backhaul, that's cellular, that I have very little experience with. But you're absolutely right. That creates its own constraints on the network and its own demands, and definitely not my wheelhouse. So
Okay.
But I will say, I mean, Juniper as a company, a big part of what Juniper does is work with the Verizons and the AT&Ts and the Deutsche Telekoms, trying to solve the problems that they have and Comcast, right, supporting more subscribers, higher speeds, lower latency. And that's a whole different set of technologies. Again, it's not my wheelhouse, so I won't embarrass myself by trying to talk about it. But I totally agree. This is definitely sort of one side of the equation. That side is just as important and probably more noticeable to the average user who, it's like, how come I don't have a connection? How come I get my email on my phone, right? So.
Okay, I wasn't sure if some of these software-defined network things tried to look outside the immediate.
So I think they do, actually. So
area.
the research I've been doing into SDN, there's definitely, so again, Google was one of the first to come out publicly and say, hey, we built this backhaul network for ourselves using OpenFlow. And from it's called the Open Network Foundation. Actually, Verizon was one of the speakers, somebody from Verizon, and they were very keen on using software-defined networking as well. So again, not my skill set, but I do know that there is very much interest because they want to drive down costs too. One of the slides that he showed is actually one that we use at Juniper, and it's showing the cost of building the network and the revenue per subscriber, right? And so once you don't make it up on volume, as we all know, right? So the service providers are just as interested in figuring out how to solve these problems elegantly and economically as big enterprises and big data centers are. So great observation, though.
I'm actually not that familiar with the data center.
Okay.
But could you give me an idea what is the latency requirement in this environment?
So
you guys mentioned a lot of latency.
Absolutely. And part of that was, so QFabric, we advertise microsecond latency, and that supports most things people are doing in data centers today. Latency is most important in a couple of, at least from an economic perspective, meaning people that are willing to pay to make it less. Wall Street, so people that in trading environments, because you can actually get a competitive advantage if you can trade a little bit faster than the other guy. So they would love latency of nothing, and they'll pay for it. They'll pay for another nanosecond of latency improvement in the trading environments. Another place is if you're building these big data centers and you want to distribute these applications that again want very instant response time from the app tier to the database tier, it's in the nanoseconds that we're striving to get to today. So that's another reason I didn't really talk about it with the virtual switches, because they're based on server architecture. They tend to have higher latency as well, even within the given physical server. You'd think, well, it's virtual and it's on the server, it should be fast, but it's those buses inside of a physical server weren't really optimized for network traffic, for network packets, and so they're actually. It's not as efficient as pushing it out to a physical switch and letting it processing it and pushing it back onto the hypervisor. So again, the products in the market today that are considered low latency are a couple of nanoseconds is what we talk about. So, but it's not important. I mean, obviously, if you're checking your email, I mean, we're talking about high-level protocols. Some of them are very tolerant of delay, right? The 30 seconds, I'll check again, right? But it's more of these. It's somewhat niche, but it's also somewhat inside the data center. again, app to database and so forth that are very latency sensitive. But it's not, by all means, not every application is super latency sensitive. So, anything else? Oh, thank you.
Thank you.